the bandwidth always is the key in both applications. So in the radar detection, we need the bandwidth for a high range resolution, and on the communication side, we need the bandwidth to offer high data rate communication. And it's really tricky to achieve that at lower frequencies. So going up in frequency allows for achieving a high bandwidth, because the relative tuning range of the devices is the limiting factor here. And at 300 gigahertz, we already demonstrated a bandwidth of around 100 gigahertz. So delivering both high resolution and high data rates. So another aspect is when we move up to higher frequencies, we can have a much higher level of integration. So we can integrate the antennas or even complete antenna arrays on chip. So this is another very important aspect, since the target devices must be tiny, small, and highly integrated. So besides the examples that I already showed, there is like the assisted takeoff and landing approach for rescue scenarios. There could also be further rescue scenarios where the identification of the tag is key, which is needed. So you can set up, for example, a reference network, and you can set up within minutes. For example, those tags could be dropped in an unknown scene and scenario and serve as a reference wherever you need, for example, to detect very weak signals in the vital sign detection area, for example. And so this is one other application that I could think of here. And where it is also very beneficial is in crowded areas, or where you have a lot of clutter stemming from metal in an industrial area, for example, where the linear radar comes to its limits because there are so many reflections from everywhere. And here we not only need the harmonic radar approach, we also need the communication for identifying who's coming in and out, or what device is there, or what robot is entering the room, and so on and so forth. I mean, of course, we have the limit in the range because of the very high free space path loss at 300 gigahertz. Still, this gives you, again, much higher resolution, as I already explained, than systems at lower frequencies. So this is making it a perfect candidate for low to medium range application, where the resolution is the important parameter. For example, when we want to detect the degradation of tools in certain machines, we need a very high resolution, but we don't need this very high range. And even if we need a higher range, there are some tricks some cards that we can play with a lens, for example, with MIMO, where we can even overcome that. And I think it's it's the thing we need to do to overcome the range issue, because this benefit of the high bandwidth really is necessary for certain kind of applications. Yeah, as I pointed out before, we are limited in the output power. We have a medium output power from our silicon germanium technologies. And in order to use different technologies to overcome this, we can use heterointegration, for example, in the future. There's right now the Apex pilot line, which is a heterointegration pilot line within the European chips law. And there, finally, we will be able to use technologies like gallium arsenide or indium phosphide to build better amplifiers, for example, LNAs with lower noise in receivers, or power amplifiers with higher power in the transmitters. And in particular, if we want to do communications together with the radar, we need linear amplifiers. So we need higher power to work in the back-off constellation with a very high linearity, for example, for OFDM radar and further applications. So that's my vision of the future, that we can overcome certain kind of problems by using heterointegration.